Hello, astronomy class. So today we're going to look at some ways that light helps us explain some phenomenon about stars. And this is all leading up to something called the Hertzsprung-Russell Diagram, which we're going to introduce a little bit at the end of this lecture, but we're not going to get very far. So what we're really going to talk about are two major concepts called, one's called the inverse square law, and then the other concept is why are stars different colors. So I'm going to go ahead and share the same slides I gave you, and we're just going to look at the slides together. All right, here we go. Okay, so luminosity and color. So the first question, and this is the question I challenge you guys with today's daily question, my attendance question, is why are some stars brighter than others? And so there are two main reasons. One is because some stars just give off different amounts of light energy. So we call this light energy luminosity. And I'm going to show you guys kind of a good way to look at luminosity in a second. And another reason that some stars are brighter than others is that the distances from Earth to those stars vary. So it kind of makes sense. The closer a star is, the brighter it's going to be. The farther away it is, the dimmer it's going to be. And this is the same thing like whenever you see a car approaching you. If the car is a mile away, at nighttime, the headlights are going to be very dim, but if they're 5 feet in front of you, you could be blinded by the headlights. Not literally blinded, but they'd be very bright. So let's look at these two concepts. So the first concept is luminosity. So remember, I said luminosity measures the amount of light energy. So stars have different luminosities, and next week we'll look at why stars have different luminosities. But it's mainly because of their size. Sometimes also could be because of the elements that they're fusing together, the type of nuclear fusion. And you can kind of think of this as like light bulbs. So when you go to the store and you buy light bulbs, there's all types of different options. Before the fluorescent light bulbs and LED light bulbs were readily available, it was just the plain old incandescent light bulbs, and you had 40-watt bulbs, 60-watt bulbs, 100-watt bulbs, and maybe even higher than that. 75-watt bulbs are kind of in the middle too. And so if you're buying a 40-watt bulb and you're used to shopping for light bulbs, you know a 40-watt bulb isn't going to be very bright. Most people get a 60-watt bulb or maybe a 75-watt bulb. If you get a 100-watt bulb, you know that's going to be very bright. And it might be a little bit too bright. A 100-watt bulb is a little bit too bright for me. Recently, manufacturers have started putting a label on it that says lumens. So lumens is the measure of luminosity that a light bulb gives off. So if you look at the bottom left of this picture, it says 800 lumens. The reason they started doing this is because LED bulbs actually use less energy than a regular incandescent light bulb. And so it says 60-watt replacement, but it actually only uses 8.5 watts. So lumens is measures how bright something is. And so when you think of stars, stars have different amounts of lumens, or they give off so many lumens depending on how much energy they're giving off overall. So how does this answer the question about why are stars a different brightness? Well, some stars are just more luminous than others. But I mentioned earlier that there's a second reason why stars can be brighter or dimmer, and that's because of this issue of distance. Now, distance, so one thing before I continue, I think I mentioned in a different video, stars are actually varying distance from the Earth. When you look up at the night sky, it might appear that all the stars are the same distance from Earth, but when you look at one star and you see a star right next to it, well, those stars look like they might be pretty close to each other, but they might vary greatly in the depth of distance. And there are lots of methods to measuring the distances to stars. I'm not going to discuss them here. We probably won't discuss them this term. Involves a lot of geometry. But you should know that astronomers do have ways of measuring the distances to stars. So a star in the night sky that looks really bright might actually not be that bright compared to other stars. It looks really bright to us because it's really close to us. But a star that's really dim might actually be really bright, but it's just really far away. And so this is all because of something called the inverse square law. If you ever study photography, you'll probably learn about the inverse square law again. Inverse square law, just look at this diagram right here. First of all, if you haven't seen the video on today's agenda about the inverse square law, I really encourage you to look at that. There's a really nice visualization. But let's just pretend that this sphere right here is our star. And so and we can pretend that this is like a piece of paper on top of our star. Now we can't put pieces of paper on a star, but just kind of bear with me here. So if we put the piece of paper on our star, that piece of paper receives so much light. And if we double the distance, that all the light that one piece of paper had would now be distributed over these 4 rectangles. So the brightness that this one piece of paper had on the left is distributed or divided in 4 to those 4 pieces of paper. And if you triple the distance, the original brightness is divided by 9. So it goes in a pattern like this. So the inverse square law just basically describes why things appear dimmer at farther distances, because, well, this sphere of energy, as the star emits its light, it emits a sphere of light or energy. That energy has to be distributed. Doesn't have that once a star emits light and that light leaves the surface of that star, or even our sun, for example, that sphere of light has no way of gaining energy. That energy is spread thin, spread out as it travels through space. And here's kind of a deeper explanation. This all goes back to how waves work. So remember, this week when you guys talked about waves, one thing we learned about was amplitude. When we think about ocean waves, the amplitude of an ocean wave kind of tells you, well, how high the wave is. Well, with light waves, amplitude represents the brightness. So again, my star and rectangle example over here, if we start with a very bright light wave and then double the distance, well, that light wave has to be split up. And the way that it's split up is not by its wavelength, but by its amplitude. So the amplitude shrinks as it travels through space. As the amplitude shrinks, so does the brightness. So to sum up this whole brightness question, even though stars have a consistent luminosity or a consistent brightness, as that light travels through space, that light is traveling over a 3-dimensional area. And once the light travels over a 3-dimensional area, the light has to lose energy because it's spread thin, kind of like spreading butter on a piece of bread. If you spread over too much bread, you lose the butter. Kind of a hint to another video you guys might be watching on today's agenda. Okay, so the second question here is, why are stars different colors than others? So we answered the question, why are some stars brighter? Now we'll answer the question, why are some stars different colors than others? So this has everything to do with the star's temperature. So every object that gives off heat glows a certain color. For example, our bodies right now, my body is glowing. My body's giving off heat, which means I glow a certain color. However, I'm not glowing very hot right now. My internal body temperature is 98.6 degrees, which is not hot enough to produce light that is visible to the human eye. I am producing light right now, but the camera that you guys are looking at cannot capture that light. However, there's a picture right here of an infrared camera. The infrared camera takes infrared light and translates it into visible light that we can see. So if it just kind of analyze this guy's heat signature, the red and white would be the hottest stuff. So his face is very warm, his hands are kind of warm, his arms are a little bit cool. So that infrared camera is measuring his body heat. Again, that's invisible to our eyes, but an example that is visible to our eyes is like a stove burner. Lots of you guys, and myself included, might have an electric stove burner. As those stove burners get hot, you can see the one in the back is black, but the one that's in front is on. So as it gets hot, as any object gets hot, it will eventually glow red. Once it's hot enough, it will glow red. And if you might have guessed from yesterday's reading, the hotter it is, the shorter the wavelength will be. So, and also there's a video on this as well. So if that burner can get hotter, I might be able to get it to glow yellow hot or white hot or even blue hot. So blue would represent the hottest color star, red would be the cooler stars. And again, there's a video on today's agenda. I encourage you guys to watch it if you haven't seen it yet. So stars come in a variety of different colors because each star has its own different temperature. Again, this has to do with the kind of material that is fusing inside of its core. So why are stars different brightnesses than others? Well, that might have to do with how luminous it is, how much energy it gives off, but it also might have to do with how far away it is. Why are stars different colors than others? That just has to do with temperature. If you guys can look at this picture here, the blue stars would be the warmer stars. Yellow stars are kind of the intermediary stars, and then red stars are the coolest. Now, if you see a star twinkle or change colors in the night sky, a lot of you guys have been going out and enjoying the night sky now that you're learning about stars. In our night sky, stars don't change color not because the star's temperature is changing. That phenomenon is because the Earth's atmosphere interacts with that light. So because we have so much air between us and outer space, the light changes as it filters down into our eyes. So for the most part, stars stay a more or less consistent color, but our atmosphere interferes with that color, which is why we see this twinkling effect, or sometimes you see looks like the stars might be changing colors. So it's not actually changing color. That's just because of a phenomenon with the Earth's atmosphere. If you were to take a spaceship, launch yourself above the atmosphere, that twinkling would go away. So why are we talking about all this? Why are we talking about why stars are certain brightnesses or certain temperatures or colors? It all has to do with different families of stars. So if I took all the stars in the galaxy and I plotted all of their luminosities, or how much energy they get off, and I compare that to the color of the star or the temperature of the star, I get to see these patterns. And that's what two men named Hertzsprung and Russell discovered when they made the Hertzsprung-Russell Diagram. So on this chart here, this is also in the CK12 reading, you'll see that on the bottom, remember the red stars are cooler, so I have 3,000 degrees Kelvin all the way to 30,000 Kelvin. Redder is cooler and bluer is warmer. And then luminosity, luminosity starts here, 0.0001 lumens, or sorry, 0.001% of what the sun's luminosity is, all the way up to 10,000 times the luminosity of the sun. So from the bottom right to left is from cooler to hotter. On the left, bottom is the least energy, top is the most energy. And once I plot all the stars and galaxies on this graph, I see these clumps. I see clumps down here, one big stream of clumps right here, then a few clumps up top. So we see patterns of how stars are formed and how stars live and die. So next week, we're going to start talking about the Hertzsprung-Russell Diagram and what it means and how it helps us understand what stars are. So stay tuned for that. Hope you do well on the quiz today. If you have any questions about anything I talked about or anything on today's agenda on the quiz, please let me know. And I hope everyone has a good day. Bye.